So just to be very clear on the plan, we are going to finish chapter 27 today.
Whoa.
Okay?
You don't even have a sign.
I know, and I'll talk about that in just a second. Whoa!
Whoa.
So we're going to finish chapter 27 today. On Friday, you will take a test. It's the way that it's structured. Let me just tell this to you because there's no reason to keep it a secret. Okay? So there's going to be a chapter 25 and 26 test. I think it's like 14 multiple choice, and then one free response question that you'll do in class. Okay? Does that make sense?
Yeah.
Mostly because all of the E&M questions put tons of things together, and so it's really hard to find a question that is just over chapters 25 and 26 because they like to mix stuff. So like I was looking through all of them, like we can only do like part A of this and da-da-da. So anyway, we're going to do one free response question, 24 multiple choice, and then I'm going to give you so this is kind of over chapters 26, 27-ish, right? Like kind of throughout what we've known, a take-home test that I think is going to be 3 free response questions, okay, that you'll take home over that weekend. Does that make sense?
Is it due
Okay.
like when we get back?
That's my plan, is that it would be due on that Tuesday or whatever.
Okay.
Okay? Jack was complaining because there wasn't any homework over chapter 27.
Yeah,
And
frustrates me.
I know. And chapter 27, I feel like it's more conceptual than it is like pounding out stuff. So I picked out 6 problems, 6 homework questions. They are just suggested homework. You do not need to turn them into me. Okay? Unless you would like me to make them do. Some of your faces are going like, yeah, right, I'm not even going to look at them. I mean, whatever. I don't care. I can collect them or not. I don't want you to be stressed out, and I want to move on. Does that make sense? And since we're going to have a test over it next time, you know what I'm saying? Like, I don't feel like there's a lot of time in between. Okay? So let me just tell you that the suggested homework from chapter 27 are, and these were just questions that looked interesting and valid and more or less doable. I didn't actually go through and do them, but I was like, yeah, we could probably handle this. We're 9, 16, 17, 20, 22, and 26. Okay? So again, that's suggested homework. You don't have to do it. On Friday, your chapter 25 and 26 homework is due. And the free response, or not free response, the problem set, skipping number 6. If you did number 6, using whatever crazy method you wanted to use, great. You can turn it into me. You don't have to like withhold it from my eyes, okay? But
crazy method on 5 too.
I don't think you needed a crazy method on 5, though, did you? Like you can always use legitimate, like non-traditional whatever. I think number 5 was doable with
It was.
non-crazy stuff. Is that true?
It was really.
Yeah, like, cause like I looked at 5 and 6 and I found the crazy stuff and I used the crazy stuff in 5 and 6.
You have to find electrical potential.
Do you on that one too? I thought you just had to have springs in that one.
You don't know enough information to do it with just.
Oh, okay, then don't. 5 and 6. Okay, shh. I don't want people to stress out about stuff we haven't talked about. So if you looked it up, if you found it, awesome, good for you. If you didn't, then don't worry about it. Is that okay? Okay, I just want to move on there. What?
Okay, so this is like not related to number 5, but it's in number 5. It says the electric field has a magnitude of 5 times 10 to the 5th volts per meter.
Yeah, don't worry about it.
Don't worry about
So
it.
skip it. That's what I'm saying. We will get there. Just don't even I don't want people to stress out about it, friends.
Oh,
It'll be fine. I didn't look carefully at it before I handed it out. I apologize. That's my fault. I will own that. Okay. So, are we clear on that? What needs to happen by Friday? What's going to happen on Friday? All of that sort of stuff. Okay. So, we are going to move on then today and finish up the Gauss's law stuff. Ready? Yeah? Psyched up? Here we go. All right. So last time we were together, we derived Gauss's law. We made a statement of it, and I think we probably put a box around it even, didn't we?
Yeah.
Yeah? And what was Gauss's law? What did we end up with? What was the statement that we came up with?
The letter.
Yeah, what do we got?
Phi
Phi, right?
Phi
is
equals
sub E.
surface integral.
The surface integral, he says, with certainty and a smile on his face. The surface integral of
E dot dA
E dot dA
and is also
equals to total charge
but it's not all the charge, it's only the charge
inside
inside the Gaussian surface, right?
over epsilon.
Okay. Life is okay there?
So epsilon naught is just like it's a constant.
It's a
right?
constant.
Yeah, okay.
Yes, yes. Correct. Okay, so that is Gauss's law. Yay, why do we care? Right? I don't know. We haven't really maybe given you motivation yet to care. The reason that we like Gauss's law is because it's nice and convenient if we can define that Gaussian surface to find an electric field in a much more convenient way than a really ugly integral like we did in chapter 26. Okay, so that's what we're going to do today. So I have two notes that were in this section that I just want to make sure we've got written down so we don't forget, and then we will go on, and basically I'm going to do, it's like 4 examples, and there's one other little concept that I want to talk about too. Okay, so 2 quick notes or 2 reminders. When we're talking about Gauss's law, number 1, hi Peyton. Gauss's law only applies, and this is really important, to a closed or Gaussian surface. Okay? Hopefully you've started to read chapter 27 in the book. The first 2 sections talk a lot about why we care about this whole symmetry deal. The thing you really have to remember, though, is it has to be a closed surface. It can be any shape of surface you want, but it has to be closed in order for the derivation that we went through last time to work. Okay?
an open surface, just
Like a plane. Right? Like that. Does that make sense?
yeah.
Yeah, yeah.
Just like-
Something that
But no
that
depth
stuff
to
can
it.
get through. Yeah, yeah. I mean, you could have a closed surface that is just a piece of paper gone with that's like this. That would not be closed because I can see you through it.
Okay. Yep.
Does that make sense?
Mm-hmm.
Yeah. So that is a surface, but it's not closed all the way around. Yeah, yeah. That's the difference.
It has to have an inside and an outside
It has to have an inside and an outside, and they are not.
connected.
Yes. There has to be something theoretically, right? Because it's all theoretical, because this thing doesn't really exist, but that divides the two. Okay?
Like a Mobius strip wouldn't work.
Right. A Mobius strip would not be a Gaussian surface.
Let's find
True
the
statement.
charge one though.
What's that?
You know how we found it of a disk? Let's find it of a Mobius strip.
You can work on that.
Yeah.
Yeah, go for that, but not right now. Let's do this first, shall we? And the other thing to note is that the electric field can't be found with Gauss's law alone. Okay? You have to know something about the shape of the field. Bless you. That's another nice way to say that when you're trying to choose that Gaussian surface, there are good choices and there are bad choices, right? And the good choices are ones where you've got some surfaces that are perpendicular to that electric field and some that are parallel, and that's all, right? We don't want to have lots of crazy different stuff going on because then it's not going to be easy to solve the equation, right? Life is okay? Okay. Issues or questions yet? Okay. By the way, my daughter had a really good time at the dentist. Okay, so it worked out okay. Everything, Gauss's law was great. The dentist was great. Everything was good. It was Miriam had a great time at the dentist. Yeah. She got a little rubber ducky at the end. Like, life was good. I know, right? You want to go to that dentist too, don't you? Yeah.
No, there's a divider over the two.
Oh,
My
yeah.
legs don't fit.
Okay. in your book, example 27.3, and the goal of this problem is to find the electric field outside a sphere of charge. And as these examples are going to lead us to the conversation as we go, yes, we have done this before. Yes, we should have an anticipated answer for this. But we're going to use Gauss's law to find it. Okay? And hopefully find that, wow, that was really easy. Okay? So we've got this sphere of charge and just a couple things to define it. The sphere has a radius r, capital R. Okay? And has charge Q on it. Capital Q. Okay? So I want to look somewhere outside the sphere. So I'm going to look at a place looking at, I'm going to call it little r, where little r is bigger than big R. Are we okay with this picture? This, I mean, we can draw a picture if you'd like. So you've got a sphere of radius big R, okay, and it's got some charge on it, and I'm looking at a place out here, and I want to know what the electric field looks like right there. Okay, so let's use Gauss's law because, well, that's the section we're in, right? So it kind of makes sense. So if we write down Gauss's law, because that's what we know how to do, we're going to write the surface integral of E dot dA is equal to Qn over epsilon naught. Well, that's easy enough. In this case, what kind of Gaussian surface are we going to choose? That would be a good choice, right? I mean, you could pick anything, but a sphere seems like a good logical choice. Because we know that the electric field is going to be going outwards, right? Radially outwards, so it's got to be perpendicular to all of those places. So we're going to pick a Gaussian surface that is a sphere. The area of that sphere we can find pretty easily, right? The surface area of that sphere. And so then we can say that the electric field times the area. Well, what's the surface area of a sphere? They say with confidence and happiness, 4 pi r squared. What r am I going to use here?
Big R.
Big R, right? Does that make sense? Because we're talking about the sphere itself. Okay. Is equal to Q in, which, oh wait, how much Q is inside that sphere then? My Gaussian sphere. So my Gaussian surface looks like this. Okay. How much charge is inside it?
Q.
Q, just big Q, right? So I'm going to actually take that in out just so that we can kind of keep defining things. Over epsilon naught.
So which E is that?
This E, right, hold on, I just want to make sure I'm understanding your question. This E right there
Yes.
is, thank you for asking that because I haven't really defined that very well. This is the electric field at the point, let me define it a little bit better, point P, a distance R away from the center of the sphere. Is that okay? Does that help a little bit more? Okay, thanks for asking that question. Okay, so then we can figure out what the electric field is. True? So we're just going to solve that for E. Okay, so what is E equal to?
So KQ
4 pi epsilon naught over r squared, right? Is that okay? Oh, but what's 1 over 4 pi epsilon naught?
K.
It's just k, right? So this is really q over r squared times k, which again should not surprise us, right? That's how we define the electric field for a conglomeration of charges, right? So that should not be a surprise to us, but it's kind of nice to know that. And it seems like that was a pretty straightforward, fast way to do that. Is that okay?
Why don't we ever use little r?
Because it doesn't matter.
Okay.
Oh wait, no, hold on. I skipped an R.
No, that's just the vector R.
No. I think I did skip an R. Thank you for asking. Hold on just a second. No, I did. I messed up. I screwed up. And I spoke wrong. This should be a little R. Okay. Back up. I screwed up. My fault. Sorry. Let me go back here.
You asked us to start.
I asked which R and you lied. It's all Jack's fault. Oh, you did. That's right. High five. Then you rescinded that choice. You gotta advocate, man.
I was like, no, it's because they all said big R.
Don't trust them. Don't trust Nathan. You know this. No. I screwed that up. That's my bad. So let's go back and make sure this makes sense. This A is the area of the Gaussian surface, right? And the Gaussian surface has a radius of little r, right, Jack? Yeah. Yeah, duh. Come on. Yeah, so that should be a little r. And that changes things, and that's actually important. So I'm glad that we are talking about this. I'm not referring to my book, but I'm like, oh, man, yeah, right. Okay, so this should be a little r, which makes more sense because this should be a little r. And that should be the right answer. And it should depend on the distance. That makes me happier now that I think about it a little bit more carefully. Moral of the story? Who are we not supposed to listen to?
I didn't even say anything.
We just love to pick on you, you know. So who do we get to blame? Are we going to blame Gabe?
Yes.
We can blame Gabe. Gabe, can we blame you for that one?
Sure.
Do you take that? Okay.
Yeah, take it for the team.
We still love you. It's okay. Teresa might have said something too.
Sorry.
Did I?
It's okay. We caught it. No big deal. No worries. Okay, life is good? Okay.
How does the surface integral work?
What do you mean, why does it work?
Like,
Is this like a philosophical question or like a...
I don't know. Like when we did it, I thought I understood it, and I went back over my notes last night. Because
Uh-huh.
I thought there was a test, and I was like, "What is happening on this piece of paper?"
Yeah?
Yeah. Like I don't understand. Like,
So, okay. So I was trying to see if I wanted to look there. I think I just want to go back here. So, okay, so AJ just said, what the heck? Why a surface integral? How does this work? Let's back ourselves up to integral calculus, basic semester 2 AB calculus. Fair? Okay. So when you are finding an integral, what are you doing?
adding up lots of little tiny things.
Adding up lots of little tiny things, right? And they could be lengths, and they could be what, right? They could be anything.
You align it too.
Is that okay so far?
Let's do that.
Yay! Stop.
So you're just adding up lots of little tiny things.
Yeah.
All that we're saying when we're talking about this whole big crazy mess is that when we do this, we're trying to define this thing called flux, which is the electric field going through an area, right? A little tiny area. And then I want to know the electric field going through this area and this area and this one and this one and this one and this one and this one. So the thing we have to add up
It's all
are
little-
areas. Is that okay?
Mhm.
And all of the areas exist on this thing called a Gaussian surface, which we defined as something that was closed. And so that's all we're doing. There's nothing magical or honestly really special about it. All that we're saying is that instead of adding up all of the little pieces or all the little areas under the curve, you know what I mean? Like if you're like from very, very basic integral calculus, we're doing the exact same thing except that the thing we care about are all of the little fluxes. So the little flux on this area and the little flux on this area and da-da-da-da-da. And we're just going to add them all up, and it just happens that they go all the way around some sort of shape.
So it's like if it was like a definite surface integral.
Hmm.
Like
Which
how-
is what this is, right? I mean, we've defined a surface.
It's
Right.
definite once you define the surface.
So it is probably true that I haven't been careful enough about writing down, like, and maybe we should. Every time we do it, the Gaussian surface is blank. Maybe that would be a better way to do this. Remember, this is the first time I'm teaching this, so I'm kind of tiptoeing through it myself, right?
I don't-
But
We can call it sigma.
no, let's not do that. I mean, we could. So, okay, so let me go back here and see if I can help you and keep asking questions. Is that fair? Okay. So, looking back at this question again, we wanted to find the electric field at point P somewhere outside this sphere of charge. So far, so good? Okay. So, the way that our good friend Carl Gauss says that we can do this is to imagine a shape, sphere would be a good choice in this case, okay, that has a radius of little r, so that it goes through P, and instead of finding just the electric field, which is what the whole goal was, let's find this thing that we're going to call flux. Okay? And that's what he says. Let's look at this flux thing. The flux thing happens to be the electric field through every little tiny little chunk. Then we're just going to add all the little chunks. And the little chunks happen to make a big sphere. Are we okay so far? That's this half of the equation.
Right.
Is that okay?
That's what I
And you
think.
can say no.
And then the electric charge times the surface area, which is all the little parts together.
He's processing. There's like some gears turning right there. So that's this half.
Okay, so when you went from surface integral of E dot dA to magnitude of E times 4 pi r squared,
Yes.
there's a step in the middle where you evaluate the integral.
It's the surface integral. So since E is constant, she's doing the surface integral of dA, which is just the area. Is the integral of dA is just area.
Oh.
And so it's the surface area.
Is it constant?
Because it's a constant electric field, so you
Right,
can
so-
pull E
so-
out.
Yeah. So when we evaluate, Evaluate this, we're doing it in a convenient way.
It doesn't matter because the electric field is always perpendicular.
exactly.
That makes sense now.
Well, okay. So I want to react to Jack's comment, and then I'll answer your question, Brian. Is that okay? So, Jack, there may have been some noise that happened near Jack, and some hand motions that happened near Jack that implied that there was magic happening. And I want to respond to that because, I mean, it is really, really convenient, right? It's really, really convenient.
It's too
that
convenient.
It's so convenient, and the reason that it works is because we were clever at the beginning, but it didn't feel that clever because it seems pretty straightforward. We get to pick whatever surface we want so that everything works out nicely. In a minute, we're going to do one with a line of charge.
So you want to wrap it in a cylinder.
And, right, so if you could, some sort of masochistic physicist may say, I have a line of charge, I'm going to make a Gaussian surface that's a sphere. Why would you do that? You wouldn't. That would not be a good choice, but one could. And then one would have a whole lot of ugly calculus to do. You see what I'm saying? Because you'd have like crazy dot product stuff going on and like whatever. They would end up with the same thing, just after a whole lot of pain and anguish. And the beauty of the Gaussian surface is that we can pick something where the electric field is constant, are you with me there? And perpendicular to some surface. Okay? Does that kind of make sense? Why not? What's wrong?
Oh, because we did the surface area of a thing in BC, and it
Yes.
involved way more things than this.
This is a surface integral.
So we can just shortcut all of this stuff.
Yes.
Yeah.
Well, because that was one thing, this surface area of like weirder stuff. It's just a sphere.
Yeah.
We already know that.
Because you can,
But
I'm not ignoring you, Brian. I just want to say one other thing.
I'm just-
So, So here's the thing. When I taught geometry to little 8th graders, and we would find the volume and surface area of lots of stuff, right? And you can find the surface area of a cylinder pretty easily because you talk about like taking the can label off and you've got your rectangle and your circles. That's pretty easy to do. And you can talk about finding the there are lots of really lovely derivations of things. When you get to finding the surface area of a sphere, there are two answers that I can give 8th graders that are not in BC calculus, okay? The two answers that I can give 8th graders are either, we're going to do an example, and I'll tell you what the example is in a second, and oh my gosh, it happens to work out really nicely, right? We've got this experiment that happens to work out that gives us 4 pi r squared. That's cool. Or, this is what the surface area is. Wait until you get to calculus, and then you'll see it. Okay, because there is not a nice way to do it like there is for a cylinder or like there is for a cone even. I mean, cones are not the easiest thing to do surface area-wise for 8th graders, but they can handle it, right? You just cut it and then it's like the little sector and blah, blah, okay? But in 8th grade, the only way that I've found to prove to them that it's 4 pi r squared is to we get oranges, which are spheres, right? Have you guys done this? I don't remember if I did this with you ever or not. Like, I don't think I had you in 8th grade. And you could like trace the radius of the orange, and you make a bunch of those on a paper. And then you peel the orange, and that's getting the surface area. And then you put the little peel into the orange, and oh my gosh, how many circles does it fill up? It fills up 4 of them. Do you see what I'm saying? It actually works pretty well.
Derivation.
It's great. I know, that's exactly what you're doing in calc too, isn't it? You peel the oranges and it smells really good in the room, right? And that's that's the best way that I've found to convince kids that formula is even halfway legitimate, because otherwise it's just like arbitrary numbers, right?
As you're peeling at the orange squirts and then it gets in someone's eye and you go to the nurse's
Well, we
office
want
and
goggles.
you're like-
Goggles.
Oh,
right?
okay.
Safety first, Teresa. But regardless, either because you peeled oranges or because you did it in calculus, you know that the surface area of a sphere is 4 pi r squared. We just go with it because we know that that's true. You don't have to do that ugly stuff because it's a given. Is that okay? Okay. Brian Richter, go.
So, right now, I'm sure there might be a different use for flux, but right now, you use the flux, so that would be like E 4 pi r squared or Q over E naught. And you're using the flux just to find the strength of the electric field at a distance r away from the center.
Yeah. So really, like, this is just a convenient thing that makes these two things equal.
Yes.
So it's kind of like when we were doing kinematics, and you say F net equals the sum of all the forces, and then you also say F net equals ma. And really, do you ever use the F net?
No.
No, it's just kind of there and helpful to make everything else fit.
And so you did
That's
that.
really all you need this for.
And so you did define E, which is the strength of the electric field at P.
Correct.
R away. At any point P.
Little r, yes, away.
Yeah.
Yeah.
Okay.
Does that get you where you need to go?
Yep.
Okay. What else do we have? What else can I answer? Nathan, you're not still mad at me because I blamed you for the big R, are you? Okay, I just want to make sure. I couldn't tell if that was a glaring thing. I know, but I think he got mad at me before I decided to blame you, Gabe, so I just want to make sure. Okay. So we're kind of feeling okay with this? Okay, now, are you ready for this, Brian? This is going to be exciting. Instead of looking at a point P outside of the sphere of charge, let's look at a point P inside the sphere of charge. Why not, right? That'll be fun. Are you excited? You guys don't sound very excited about this. I think this is really cute because then we get to graph it and it's really lovely. So this is from your book, example 27.4. Here it comes.
Oh yeah, this is all where it's linear.
Don't give it away, Gabe. Jeez. Spoiler alert right there. Okay. We want to find the electric field inside a sphere of charge. It's the same sphere, but let's just make sure we define everything, because I'm not always good at defining things, so I'm going to work on this today. Okay, sphere of charge that has a radius, big R, and it has charge Q that's distributed throughout this thing. Okay, so this is not a conducting sphere. This is a rubber ball that's got a bunch of charge in it, okay? So let's draw a picture. So we're looking at, so here's my sphere. I want to look at a point. We'll say point, not point. P.
Pants.
Ah! You guys are so cranky. Jeez.
Calculate the E field
What kind of Gaussian surface would you pick for that? I don't know. Maybe 2 cylinders?
Depends if the pants are flat or not.
I suppose, yeah.
Zoom out and it's a point
Rectangular
charge.
prism.
There you go. Good answer.
Multiple.
Point P. A distance r away from the center. But now r is less than big R. So this has a radius of big R, and I'm now looking at a point right here, little r away. What kind of Gaussian surface should I pick this time?
Sphere, triangular.
You could do that. You go have fun with that. I'm going to go with what Brian said, because I think that's a good choice.
Go W-E good.
I'm thinking that a sphere would be a good choice. A sphere with a radius little r, right? Okay? And to be very clear, I want a sphere that is concentric with the center of this sphere, right? Not just any random sphere. You could have a sphere
I'd
like this.
To make the sphere like go completely
No!
outside.
Has some velocity that's going. No, that's a terrible plan. Bad idea. So we want a concentric sphere.
Can we
Okay.
center the sphere at point P and then have it have radius big R?
You can do whatever you want. I've not written out that one, and I'm not confident that it would be easy. But because we don't know how big little r is, we don't know that's halfway, right? So then, yeah, I mean, there's a lot of unknowns there.
No, it would have radius big R.
Which means you'd be on the circle.
And it should
No,
be
bad
outside
plan.
the circle.
Bad plan. Okay. So the whole game here is to use Gauss's law. So let's use Gauss's law. Gauss's law says that the electric flux is equal to the surface integral of E dot dA is equal to Q inside, and that's important. So that is no longer equal to big Q. Do you agree? No longer equal to big Q. Important, important. Wah, wah. Okay? And epsilon naught.
I made it.
It's so nice to see you, Logan.
I think it took me a record hour and 15 minutes to get here.
Wow. Well, we're glad you're here. Glad you're safe.
What were you doing?
I'm the jack.
Moped?
Okay. So, we're going to recommend, Logan, that you watch the video from last time, too, because
Yeah.
otherwise you're like, I don't know what that is. But we don't worry about them. They're not bad, right? Do we agree? Not bad.
They're
They're
not
terrifying.
All right.
It's like the dentist all over again.
Okay.
Traveling through time?
Stay with me because we don't have tons of time here, friends. So, E dot dA, our electric field is going to be constant everywhere up there, right? Okay? And the surface area of that sphere, even though it's littler, it's still the same formula for surface area. Okay? So is everybody okay with that surface integral? Just equaling E times 4 pi. Jack, should this be big R or little r?
Little R.
Yeah.
Are you sure? Does that get me an A in the class automatically?
Automatic A just for knowing if it's big R or little r. Yes. There you go. You're welcome. Okay. Now, what's up?
Could you write Q inside as Qn times little r over big R Q?
Wait, well, which happened there?
You just write Q inside as Qn times little r over big R Q.
We are going to get there, yes. We're just not quite there yet. Hold on to that for just a second. Because that's about where I was about to go, but I just want to make sure that we're okay with this first. So Nathan is wanting to get rid of this Q inside business, right? And everybody else is like, yes, let's do it. So we can kind of look at this. I'm going to take it in 2 smaller steps just to make sure that everybody's there. But remember, we defined rho a couple times ago, or maybe it was just last time, I can't remember now. And rho was equal to
Volumetric charge.
charge per volume, right? Does that make sense? Okay. So that could equal the charge of the whole sphere divided by 4/3 pi times, is that going to be big R or little r?
Jack? What? It's gonna be big R.
Yeah. Or we could write that as Q in over 4/3 pi r. Whoops. Which r should that be?
Jack? The
I don't know, that grade's gonna slip now, Jen. I don't know, this is not good. Okay, is this statement okay with everybody? Okay. So now, instead of writing Q in, which we don't know, we can write Q in terms of stuff we do know. We agree that the 4/3 pi's are gonna go away?
Yes.
So we can say, as Nathan said before, go ahead and tell us what Q in should be then, Nathan.
Qn times R over R, little r, over big R cubed.
So something like this. Is that okay that I wrote it like that? Is everybody okay with that?
Where's the epsilon? Oh, there's it.
I put it there. I could have moved it over there. I mean, whatever. So now we can come up with an expression for electric field. So it's the electric field inside or at a point P that's a radius little r away from the center of this charged sphere. E is going to equal, well, let's not try and make this too messy, shall we? We've got a little r squared here, and we've got a little r cubed here. So what's going to happen with those? We're going to have some canceling going on, right? So we've got, that's going to be like 1 over 4 pi epsilon naught. That's nice. Times Q over r cubed. Correct me if I'm wrong here, friends. Times r. Does that look okay?
Yeah.
So epsilon naught we know. Big Q we know that's the charge in that sphere, in the big one, on the whole ball. R cubed, the big R is the radius of that object. And the electric field does vary depending on the radius. Okay. We okay? So we're going to put a box around that because that's important. And then we get to put these things together, these ideas together. I've seen this graph on the AP exam more than once. And I'd like you to draw it right now for me.
Is this the answer or the question?
Yes. I don't know. I don't know what you're thinking, Gabe. I'm not there yet.
I mean, like, on the AP test.
It asks you to graph this a lot.
Okay.
Yeah. It asks you to graph the electric field as a function of R, okay, for a uniform charged sphere, okay? This is the radius of the sphere itself. So go ahead right now by yourself and see if you can graph that, and then I'll let you compare in just a minute. Why don't you check with your neighbors and see if they got the same graph you did?
It's linear, it's r, and then it's inverse square.
Yes, because R squared, right?
Wait, inverse square.
Yeah, like 1 over it's good.
Right.
Right. Because this has a slope of kq over big R cubed. It's 1. And then the other one, that's bigger, is an inverse square. K cubed. That's what you get. So little r square.
Okay.
No, I didn't use R.
What? Yeah. You can write it piece
Yeah.
Q over R squared.
Because it's doing continuous too.
I think
You could do a line with L over it.
Gabe and his line girls today. All right. How we doing? Did you get it? Isn't it nice? Teresa, what does the first part look like?
A line, the positive with its positive slope.
Positive slope, something like this.
Yeah.
Something like this. And then, Andrew, what happens after you get to R? Does it keep going? Well, let's take a look. Okay, so let me ask first, are we okay with this part? This is the inside part. So it's got some sort of constant times R, so that's just going to be a line, right? So the slope is going to be this big nasty stuff, but it's just aligned with the slope of that stuff. What happens after that?
It's an inverse square type thing.
These are constants, right? So it's like a 1 over r squared. What does a 1 over r squared look like?
1 over r squared.
It looks like 1 over r squared, says AJ, right?
Well, I mean, that's,
It's going to decrease.
it
as r
decreases
approaches
at a decreasing rate.
Inverse
Oh.
square.
Boom. That's what we like to call physics slam dunk.
Do we?
Sure.
The Jack Logs of the world call it that.
Something like that.
Hey, you know, there are two of us.
There you go.
My grandpa.
Okay.
All right. Are we okay? Issues, questions? Can I help
There's
you?
an arrow.
No, it just ends right there.
Is that better? Okay.
It's just 0, right?
All right. Next. This is what Teresa won. This is why Teresa came today. This one right here. 27.5.
Okay.
Find the electric field due to a long charged wire, right? This is the one you came for, I think, isn't it? Yeah. So, infinitely long wire, we're going to call it infinitely long because the ends aren't going to matter if we're close enough to the wire, it's okay. Okay, same conversation that we had before. So you've got a charged wire. Let's say it's positively charged, just so that I can write something down. And I want to know the electric field due to that wire. Okay? If I was going to choose a Gaussian surface for this, I mean, let's kind of define things. I guess we can talk about it as a certain length of wire or not. It doesn't really matter. What kind of Gaussian surface might I choose to find the electric field due to that wire?
An octahedron.
I'm going to go with Brian. He seems like the most reasonable one of all of you today.
I believe that it's the, will be the
I'm going to choose a cylinder, centered.
Actually,
Guys, stay with me because I don't have a lot of time now, and Friday is Friday, regardless of how far we get. So we want to get through this stuff, right? Yes, please. All right, so there is my cylinder. It's supposed to be centered like on the line. It doesn't quite look like it, but you get the idea. Okay? We want to know the electric field. We're going to start, as we have every problem today, with Gauss's law. And this one, because we've chosen a cylinder, this isn't going to be quite as easy as we had last time, right? And the last problem. How many different surfaces do we get to talk about in this case?
3.
3 surfaces.
But at the ends, it doesn't matter because the electric field is parallel. to
Right.
the
Oh my goodness. Hello. That was like a really big surface integral. Like, you're not afraid of me, ah!
That's how terrifying it is. When you least expect it, it comes up at you.
It's going out like this, right?
If the wire is infinity long,
It is infinitely long.
then the
So
Isn't this like the problem we had before, though?
that's why you're here.
Yeah.
Because this is going to be so much faster and so much easier.
No, I mean the last time we were here.
Yeah.
Yeah. Okay.
No, 2 times ago. Chapter 26.
No.
Oh, no, we did
one
something
just
like this.
Oh, yeah. We didn't finish it.
We didn't.
No, we didn't actually find the electric field, I don't think.
I thought we did.
Did we?
Yeah.
Oh, Gauss's law.
No,
just found the
We didn't use Gauss's law.
no, we did something with the cylinder, but it wasn't like this.
Yeah. We started it's like we started this problem, we didn't actually find the electric field.
Okay.
I promise. I just looked at my notes. All right. Because, and let me tell you the reason that I know that. Because when we did the problem, we only knew this half. We hadn't established this yet.
Okay.
Yeah. So all that we were doing was finding the flux.
Oh, okay.
And you can find the flux, and we're going to do that right now. And the whole point of doing it before was to say that the bottom and the top don't matter, right? And everybody's okay with that now. Except for our friends that maybe weren't here last time. They're going, I need to watch that video. Yes, you do. Oops. The flux for the top. The flux for the bottom. And the flux for, what do you want to call it, AJ?
The lateral.
Okay. I think in the book they call it the walls, but you know, whatever makes you happy. And is that okay with everybody? So we're really going to find the flux for each of these, which means that we have to find the surface integral for each of those. We'll get there in just a second. Is going to equal still Qn over epsilon naught. If you take the surface integral of this top piece, this one here, what's phi going to be? What's the flux going to be? 0. Because the electric field is parallel to the surface, so it's perpendicular to the area vector, right? What about for the bottom? Same story. So really we only need to deal with the lateral face. So we can write a surface integral just for that part. Let's do that just so that we're staying and we're being really good kids. But we don't have to freak out about that because it's always going to be perpendicular there, right? So that means the electric field, and because we chose a Gaussian surface has its center where the line of charge is, it's going to be the same everywhere, which means it's just going to be E times A. So that's just going to be the electric field that we don't know yet times what's the area of the lateral face?
2 pi r.
2 pi r, little r, I just wanted to find that r, times the height or the length or whatever you want to call it. I don't care. Does anybody care?
H.
H is what he wants. Just chill out. Equals Qn over epsilon naught. Now, I don't really know what Qn is, do I? We haven't really defined that, but we do know that convenient thing, that lambda, right? The charge distribution, the charge density is equal to Q over L, or in our case, H. Is that okay? So instead of writing Q, I could write lambda times H. Over epsilon naught. And that's why we don't really care how long that thing is, as long as we're not worried about edge effects. So I've got E, my electric field. Well, my H's are going to go away, it looks like. And so I'm going to have lambda over 2 pi r epsilon naught. Is that okay? And if you look back at chapter 26, when we define the electric field of a line of charge a distance r away, that's exactly what we got. This to me seems easier.
Where do we get the? Can you change that 2 pi?
Hold on. One thing at a time. Go back there.
Lateral surface area.
Just like the rectangle.
If that's the circumference, which would be one of the 2 parts of the rectangle that you form. Of the Gaussian.
The Gaussian surface is a cylinder, right? Is that okay?
Yes.
And so when you take that into 3 pieces, you got the 2 circles that don't matter, and then the rectangle. And the rectangle is 2 pi r times the height.
Okay. Are you just that? Yeah.
Is that okay? Are you okay?
This is the algebra.
Yeah.
Could you turn that 2 pi e naught into a k if you wanted
With
to?
a 4, I mean you'd have to put another 2 in there.
Yeah, you
It's an
did.
Yeah.
epsilon. And then, sorry, it's an epsilon.
You did.
Yeah.
Not E.
My bad.
Yes.
I mean, that's the Greek.
One more. 4 more minutes. We got to do it. So that Teresa doesn't have to memorize stuff anymore. Just looking out for you.
You're making the epsilon sound right.
Plane of charge. So now I've got a bunch of positive charge hanging out on some sort of sheet.
Isn't that different than what we derived?
I don't think so.
Like, isn't going back to the line of charge, isn't that different than that derivation from 26?
I don't think so. I can go back and look. You can go back and look. Pretty sure it's not.
It might have to be.
It's snowing.
That's the guy who doesn't know what we're doing.
Off the road.
Why don't you look it up, Andrew? I'm going to keep going because I want to make sure we get through this. We only have 3 minutes. Fair? So you look it up. Do it. Here we go. Last thing. Jack, stay with me. Logan, stay with me. Oh my goodness. This one is kind of interesting. We did this one also in chapter 26. Okay? We want to find the electric field from the plane of charge. So where is the electric field going?
Away.
Away. It's going like in this direction, right? And in that direction from the other side. Does that make sense to everybody? Okay, so it's going outwards from that surface that's got a, in this case, positive charge. We want to find a good choice for a Gaussian surface. A sphere is not a good choice. Would we agree? Okay.
A cylinder.
You could use that. I was going to choose a cylinder.
Then you could sink it through.
Oh, yeah,
so-
Right, and that's the clever thing that you really have to kind of think through here. The cylinder we're going to use, and I'm not good at drawing, so I'm going to try here, is going to go through here, and it's going to go back into here. Do you see what I'm saying? So it's going to stick through that line of or that plane of charge. Why is that a good choice? Why is that a convenient choice?
Because you can get rid of the most annoying things.
You what? What was that? Too many words. Somebody speak.
It gets rid of a lot of term.
It gets rid of the lateral stuff, right? So phi sub e is equal to the lateral, or excuse me, is equal to the surface integral. Same thing we keep writing. Q in over epsilon naught. We're going to break this down into 3 pieces again. So this is the top, and the bottom, and the wall or the lateral equals Q in over epsilon naught. The wall goes away. Now, we did a problem kind of like this last time with that box. Do you remember we had the electric fields going through, and we said that the flux was 0? But in this case, it's not 0 because the electric fields are going out both directions. So it's really going to be like twice the flux of one of them. Does that make sense? Because the electric field's going out this way, so flux is going to go this way. Flux is going to go that. So we've got twice that. Equals Q in over epsilon naught. So that's going to be equal to twice the surface integral of E dot dA. And what A are we talking about here? Just area of the circle, right? Yeah, and it doesn't really have to be a circle, but it works for it to be a circle. That's fine. So we're going to go like that. So that's really going to be E times A times 2. Now we got to get rid of this Q in business. But luckily, we've got our eta. And eta was Q in over, it's the area. So really, whatever area that is, we don't care what it is. So you can make it your rectangular prism or your triangular prism or whatever. It doesn't matter. Okay? Because now you've got 2 times E times A is equal to eta times A over epsilon naught. We can solve for E. Those A's are going to go away. And so you've got eta over 2 epsilon naught. Boom. Wasn't that nice? And it works just the same way. Okay, so just to reiterate, there is actually one section we haven't covered yet. We will get there. I don't think you won't need it for the test on Friday though, so I'm not going to stress out about it, okay? Hopefully I will see you on Friday. If I don't, you'll still have a test. Your homework is still due. I'll put this thing back up here. Critique, can I move that? Is that okay?
Problem sets due Friday.
Problem sets due Friday. Skip numbers 5 and 6. Because I don't want you to stress out about them. Have a wonderful day. Drive carefully, please.
Yeah, definitely. I'm gonna spend more time in the car than I will actually.